Okay, as I said for that example, in continuous time, let me write down some summaries. In continuous time, our closed loop transfer function I s over I star s, the resulting transfer function should be equal to s plus k in denominator. Denominator is equal to k. Assuming the perfect parameter estimation. In real world, the parameter may not be always perfect to estimate. So in real world, you should spend some time to analyze the parameter sensitivity. In this case, it may not be over the system. But ideally, this system is firstly, it must be a stable system. It should be stable for any control parameter k decide from k close to 0 to k close to infinity. No matter which k, it should be always a stable system. 0 k to any value, any value of k, the system should be always stable. Ideally, it will not diverge. It will be always a convergent system. Second, not only a stable system, if our parameter estimation is correct, it will be always overdamped. No oscillation system. Again, for any k, for any controller gain k decided, it will be always a stable, no oscillation over that system in continuous time. How about in discrete time? Based on the linear approximation, the overall control block diagram, I write again this block diagram here. It should be including CZ and SDZ. Right now, the overall closed loop controller, the input is our current command, output the sampled curve. So this system in digital domain, the transfer function, the ratio between output and the input, based on the Mason's principle, is equal to CZ. SDZ, 1 plus CZ, SDZ. Okay, so if we want to analyze all the closed loop system, we should figure out this closed loop transfer function. So how about CZ? What's the corresponding CZ? Is over there, based on the bilinear transformation, is equal to K L plus T over 2. 1 plus Z minus 1 minus Z minus 1 over R. for the system stability analysis and the dynamic damping ratio analysis, I prefer to use Z form instead of Z minus form, Z plus form, because in this case I can figure out the corresponding denominator pole, which is called a characteristic equation. So in this case, I reformulate the overall closed loop controller as the Z form, the transfer function, is equal to the denominator is equal to Z minus 1. The denominator log hat plus T over 2 R hat Z plus minus log hat plus T over 2 R hat. Okay, it should be like this. This is our transfer function for our CZ controller. How about new system dynamic? You still need the knowledge to derive the new system dynamics. Some knowledge in midterm exam. How to find the open loop transfer function. SD Z is equal to the Z transformation 0 order Hall. Please remember the 0 order Hall in NSD. Last year, I remember no student did that, but the year before last year, in final exam, there are still some students forgot this 1 minus exponential minus T over S for their NSD Z development in final exam. In final exam, some students, they still give us the wrong NSD. If you are a teacher, if you are a grader, how to give you a partial credit if you still give us the wrong NSD. It's very difficult for us to give you a partial credit because your NSD is wrong. Your NSD is wrong, so all the analysis will be wrong. Okay, so please remember how to the development process for open loop transfer function NSDZ. And the GS is equal to 1 over LS plus R. Are you going to use method number 1 or method number 2? Do you prefer to use method number 1? You can bring the handout number 1. Follow the step by step. Final exam, it should have the time limitation, so I recommend you to use method number 2 because you can easily to find this in the Z table. So I give you the resulting transfer function. It is equal to 1 over R. Now, 0 internal feedback. Z minus one over R. Z minus exponential. First order system with non-zero feedback, it should include an exponential function in their Z domain. T over L minus R. Actually, from your project number 1, you should be familiar with this transfer function. Okay, some simplification for the parameter definition. Rho over R, we define this as the electrical time constant. Okay, from your automated controller. I believe you should be familiar with the time constant. So it should be exponential minus t over tau z. Over tau. Okay, so you have CZ, you have NSD. You can use the simulation tool from handout number 5. Handout number 5, I have a Rho-Lucas simulation tool. You just need to check the pole location and the zero location. The MATLAB can help you to find the Rho-Lucas. In here, because this one is just the first order, I think I can calculate this one. So let's do a Rho-Lucas analysis. In continuous time, should be always over there. How about in discrete time? So let's check CZ. CZ0. PI control issue contain a 0 and a pole. This 0 is used for pole 0 cancellation. So the corresponding 0 location for CZ, it should be Z is equal to L minus T over 2R for bilinear transformation. L plus T over 2 times R. CZ PI control it should contain a pole as Z is equal to 1. How about NSDZ? First order system, similar to continuous time. Here, it should contain additional open loop pole location, which is this one. Z is equal to exponential t over tau. First time, when you see this, you will realize the pole is located as Z is equal to exponential minus t over tau. And then the controller 0 is located here. This is exponential function. This is a linear fraction number. Can these two be equal? Even you have a perfect L and R parameter estimation. Z is equal to exponential function. Can this be equal to a linear fraction number? Yes? Yes? Yes or no? Exponential number, exponential function, it will be a very long fraction number. But this is just a linear function. But if you don't believe this, in this case, this means you will not be able to achieve the pole 0 cancellation. But I'm going to show you three different conditions. Because we have a parameter. We have a parameter T, L, and R. So I'm going to show you some conditions. First, if we want to analyze the pole 0 cancellation performance, we should define this parameter with some actual value. So first one, on my note, we have two parameters, L and R. So we define tau is equal to L over R is equal to 1 over 1, which is equal to 1. It's easy for us to do the math calculation. In this case, L is equal to 1, R is equal to 1. All right, then I define a sample time. Sample time in this case, I am going to use a very high performance computer. So I have a sample time which is equal to 0.0001 second. If you don't know how short this sample time is, you can use the UV transformation. For this 0.0001, it should be equal to, for mu microsecond is equal to 10 minus 6. So in this case, it only have 1, 2, 3, 4, 5, 6. I use a computer. The sample time is only equal to 10 microsecond. A very fast sample time. Okay, let's check the performance in continuous time. This is a raw Lucas in continuous time. It can achieve the pole-zero cancellation. However, in discrete time, in this case, the CZ0 is equal. I should calculate the NSD pole first. So NSD pole. For condition number 1, in this case, the NSD pole location Z is equal to exponential minus T over tau. And the tau is equal to 1, T is equal to 10 milliseconds. So it's equal to exponential minus 10 milliseconds, 10 or microseconds. So microsecond, 10 minus 6. This is equal to, from my note, is equal to 0.9999. You can use the calculator to do that. Raw Lucas analysis in Z domain. The red one is the closed loop pole location. Closed loop pole location is located here. The red one. Open loop pole, sorry. If our CZ0 can locate in this exactly number, which means he can do the pole-zero cancellation. So let's check about the CZ0. CZ0 is equal to Z is 1 over 0.0001 over 2. 1 plus 0.0001 over 2. Okay. My student is calculating this number. So can you show me the number for this fractional equation?
0.9999。
And the PI control. PI control, it has additional 4 location here. This is another 4. So actually, the linear approximation under this very high performance computer control with the very short sample time, the whole zero cancellation accuracy can still achieve. Okay, second, the first one is okay for zero cancellation, so it should be stable for any k, because when you increase this k value, your row locus will move from here, k close to 0, k close to infinity. Still over than system. If you have some question, please use the handout number 5. You can use handout number 5. Handout number 5 will show you how to plot the row locus using MATLAB. As long as you have this SD pole and the CZ0 and the CZ pole location. Okay, so for condition number 1, it is okay. How about I increase the sample time? You cannot have this high performance computer. For my notes, the condition number 2. For condition number 2, the same, L is equal to R is equal to 1. I keep the parameter as the same value, and the only difference is the sample time. And this time, for my note, I use 0.2 second. I think this is not a good computer at this time. Your sample time is limited at 0.2 seconds. So in this case, the NSD pole, the pole location of new system dynamics open loop transfer function, it can also change with respect to your sample time. So you need to calculate the NSD pole again. NSD pole location in this case is equal to Z is equal to exponential minus T over tau. Exponential minus 0.2, so it's equal to 0.8187. When you increase the sample time, the open loop pole will move inside. Point 1 at 7. How about CZ 0? Our controller 0. You will find the pole 0 cancellation will start to lose its accuracy. So it is equal to 1 minus 0.2 divided by 2. Divided by 2. How about the number for CZ0? Is equal to 1 minus 0.1. 0.9. 9 divided by 11. Okay, we have some difference compared to these two numbers. We find a little bit difference. It appears at the minus 4 digits, and the 0 is the same. Sorry, the 4 is the same. Z okay, so in this case, I don't need this one. In this case, okay, this case, although the difference is very small, but I use this case to show you if you cannot achieve the pole 0 cancellation, what happened. So I will increase the error between the NSD pole and the CZ0. So for the NSD pole here, the NSD pole location is a little bit close to our unit circle, and for CZ0, will be a little bit inside the original 0 point. Like this. This is defined by 0.1 and 1,2. And this is 0.1 and 1,7. We still have a pole from our controller. Assuming we have the error, in this case, a little bit higher sample time. What is the raw Lucas like? You cannot achieve pole 0 cancellation. Go back to your automatic control knowledge. The raw Lucas is 2 pole 1 0. We can find the raw Lucas by a raw Lucas in the real axis first. So here should be a raw Lucas. But we will not have a raw Lucas between this 0 and the pole. Right? If you don't believe, use the MATLAB. You can use the MATLAB to simulate this. So raw Lucas will like this. It will be a little bit different. Also, we can meet the requirement for first one. Still stable. Is still a stable system, but what is this? some summary. When you increase the T sample time value, when K is small, K close to 0, okay, this is still an overdamped system. But we cannot have a very high dynamic response, low bandwidth response. How about K we slightly increase to a median value? I don't know the actual value because if you want to know the actual value, you have to do the simulation. But if you slightly increase the K, median bandwidth, you will figure out the system will have oscillation property. Because right now you will change to underdamped system. Underdamped means the oscillation. And this oscillation property, it should not occur in our continuous system. But after our approximation, with the limited sample time, we start have the oscillation property. Interesting thing. A very interesting thing. If we continuously to increase the K, for example, K high bandwidth control, the system will go back to overdamp again. The system will go back to overdamp again. But you will have this. Underdamped. Underdamped property. Underdamped property. Close to 0. How about the last condition? I continue to increase a very unacceptable T. Well, it will happen. You will very close to your project number 2. L equal to R. 1. But the T is 10 seconds. I only do a sample every 10 seconds. So I give you a number directly. In this case, the NSD pole is exponential minus 10. Exponential minus 10. It will become exponential minus 10. A large negative power number for exponential function, so it will close to exponential minus 10, it will close to 0. How about our CZ0 location? Z is equal to 1 minus 10 over 2, 1 plus 10 over 2. It will become minus 0 in the left hand, which means oscillation must include 0.6667. Okay, so I write down the final raw Lucas here. closed loop all location. The 0 is under here. Oh, sorry, it should be minus 10 minus 1 minus 10 over 2. And we have additional pole location here in the 1. Why is the raw Lucas like? It was similar to this one, but similar to this one, but you will not have the overlap property at the high gain, high K, because eventually you will leave the unit circle, the system will become unstable. This is the stable area. And this point is called a critical stable point from your automatic mechanics. If you have the MATLAB, you have a computer, you can calculate the critical stable K point. Low bandwidth, still the overdamped system. But when you slightly increase the K value, it will become underdamped system. Continuously increase the K value, different to the condition number 2. For condition number 2, you will go back to overdamped again. But for this unstable sample time, system will directly become unstable. So when you use the method number 1, condition 1, 10 microsecond sample time. Pole-zero cancellation is okay. Linear approximation performance similar to a continuous time. Increase the sample time, oscillation property, underdamped property occur. Continuously to increase the sample time, system will eventually become unstable at a high controller gain K. This is the limitation for linear approximation methods. So I write down some summary here. For today, I only use bilinear analysis, bilinear approximation to show you the difference. But you can check the backward and the forward methods. Similar result, just a little bit performance difference between the sample time. But for the all the linear approximation, they are all the same. Also, I only show you the bilinear approximation, but the performance should be all the same. And eventually, the closed loop controller, our result resulting closed loop controller. Based on this approximation, the design accuracy the design accuracies depends on our sample time, our digital interface T. So how to make sure our approximation performance can close to our continuous time? How to make sure? T should be as small as possible or as high as possible. T should be based on the exponential function close to or almost close to 0. This assumption, when our sample time t close to 0, it results in best approximation performance. Third, for your homework, if you are very interested in this linear approximation, compare the performance difference you can try to compare the two non-ideal performance versus the continuous time, which is the first one, critical stable point. Critical stable point as well as the oscillation, transient oscillation, which is the underdamped. These two non-ideal attributes, they may appear for the linear approximation, but you can compare these among in this lecture. I only show you the bilinear, but you can compare forward, backward Euler, and the bilinear. Using the handout number 5, you can plot the Rohr-Lucas. You can compare 3 approximation performance. Okay, so with that, I think I finished the method number 1. Let's take a 10 minutes break. For the third hour lecture, I'm going to introduce the method number 2, the red Z-domain design. Okay, thank you.